Welcome to E Squared Emporium for all things AP Psychology. Today we will be looking at how neurons communicate. Part 3, Neural Transmission. So this chart came from the Myers textbook. It shows you everything we're going to go over today about how neurons communicate. So important to remember this is indirect communication. It's like two trains passing. They're not actually on the same track. They do not directly connect. You're picking up and dropping off passengers. Our passengers are called neurotransmitters, or they could be drugs, and they're on different train lines. There actually isn't any touching happening. Within this space, we call that the synapse, and it's full of cerebral spinal fluid. So again, we'll go into more detail with the synapse another day when we get to neurotransmitters, but you see the gap there, the gap in this picture. So you see that they're not actually touching, and the neurotransmitters or drugs are going to live in that synapse. They're going to live in that cerebral spinal fluid and get absorbed into the next neuron. So again, neurons do not ever actually touch each other. That space in between is called the synapse. It's 1/1,000,000th of an inch between each, and the neurotransmitters cross the gap in 1/10,000th of a second. That's how fast this is going to be happening. I can't tell it to you in 1/10,000th of a second, but that's how fast this is happening. So we start with resting potential. The neuron is resting. It's chilling. It's hanging with the other neurons. The usual charge when it's resting is -70 millivolts. And then we have a sodium-potassium pump in the soma, in that nucleus area, the cell nucleus, and it contains more negative ions, potassium, which we write as K, and the pump regulates the nucleus and pumps the sodium out. That's Na, sodium, positive ions. So we've got negative and positive and a pump that's constantly keeping that balanced, except for when it doesn't. When it doesn't keep it balanced, what we have is called depolarization. So we're off balance. There's more negative ions inside the neuron and more positive ions outside. The cell will stop pumping that sodium out. The sodium-potassium pump stops. Positive ions rush in, and it reaches plus 40 millivolts. So now the cell's potential has changed from negative to positive, and it's been depolarized. It's like when we pull you off balance, right? You're walking just fine and somebody comes along and pushes you or pulls you off balance. You're depolarized for a few minutes. So this is what we mean. It's off balance. You're going to cross the absolute threshold. The absolute threshold is the tipping point. It's like when you tip the first domino, you can't take it back. All the dominoes are going to go. And that's what happens once we cross the absolute threshold. So we go from -55 up to plus 40, plus 50. Different textbooks disagree. And the pump stops, and now we're going to be looking at our neurotransmitters. So again, it's like being on a seesaw, and all of a sudden you get stuck either up top or you get stuck down below. You've crossed the absolute threshold, you've crossed the tipping point, right? And now you're off balance, and now the neuron is going to fire. This polarization causes an electrochemical reaction. It's electrical inside the neuron, it's chemical outside the neuron, and it literally fires electricity called action potential down the neuron. So again, here's an example of action potential and how it's going to move all the way down. We call this the direction of neural impulse, moving towards the terminal, not towards our DNA. And when it hits the end, when it hits the terminal buttons, that's where our neurotransmitters sit. That's where the drugs sit. And we're going to release them. The buttons are going to release. And then the neurotransmitters are free to float around in the cerebral spinal fluid, and they'll travel in the synapse and they'll get picked up by the next neuron. So that way they're constantly being picked up and released and picked up and released and picked up and released. Now, we need to have a little bit of a moment here before we can do anything. Our neuron can't go right into action after it's fired. We call this refractory period or absolute refractory period. It's the time that it takes to get back to resting potential. It's the time it takes to get ready to fire again. So we go from a -55 to a plus 40, back to a -55, And all this happens in a nanosecond for the myelinated axon, 1 nanosecond. So what is that like? Think about the old time muskets, the really old muskets. It took some time to reload them. That's your absolute refractory period. You had to stop, you had to reload before you could fire again. Think about when you come to a stop sign and you're supposed to let that car rock back before you hit the gas again. That's absolute refractory period. Think about when we refill a toilet. You can't just keep flushing and flushing and flushing. It needs a moment to refill with water. That's absolute refractory period. Think about the time that it takes for you to reload a sneeze. You've sneezed, and now you got a second one coming, and it takes you a couple minutes to reload that one. Right? That's absolute refractory period for a neuron. Now, reuptake is when we're going to reuptake more neurotransmitters, just what it sounds like. So now we're ready. Now all these new neurotransmitters are released into the synapse. They've been secreted and released from other neurons. They travel in the synapse and they are going to refill the little spaces that we have there at the end of our terminal buttons where we have what we call vesicles. And only if they fit, we'll talk about a perfect fit next time. And this is called reuptake. We reuptake new neurotransmitters. And this process is repeated 1,000 times a second. So if you're exhausted, imagine your poor little body. This is why we're so tired at the end of the day, right? Because 1,000 times a second, we are doing this entire process over and over and over and over and over. And this is what it looks like. We're going to look at this chart more in class. So you can see the absolute threshold, you can see depolarizing, action potential, repolarizing, refractory period, back to resting state, and over and over and over again with our voltage on the side, our millivolts. It is an all or none response. What do we mean by that? You either fire or you don't fire. The neuron will either completely fire, completely have an electrochemical reaction, or it won't. There is no part way. There is no halfway. It's going to go or it's not going to go. And what does this mean? Well, this means it doesn't really have to do with the intensity of a drug, and that's whether it's a neurotransmitter or whether it's a drug the doctor prescribes for us or it's a street drug that we're going to talk about. It doesn't really matter the strength of the stimulus. It doesn't affect the fact that that neuron's going to fire or that neuron's not going to fire. So just so that you know that every neuron is going to fire with the same exact intensity every time. We call this entire process neurotransmission or neural transmission. Neural transmission is the long way. Neurotransmission is when we shorten it. The process by which neurons communicate with each other, sending these signals through the electronic impulse or the chemical messengers. The chemical messengers are going to be our neurotransmitters. And the direction of impulse, as I've mentioned, it's the direction that the energy travels, right? It goes away from the soma, away from our DNA. It's one way only. This is a one-way street. We do not want the electricity to go back into the DNA the wrong way. It can only travel one way. That's our direction of impulse. Now, a reflex arc, also known as a spinal reflex, sometimes when we're in danger or sometimes we just need to act quickly, so a signal can be sent from a sensory organ directly to the spinal cord, and it's literally going to skip the brain. You can see where I put the yellow arrow here. That's the shortcut. Think about when you play a board game and you get to take a shortcut. Your decisions don't have to go all the way up to the brain and have conscious thought and have a debate. Should we do this? Should we do that? Sometimes the body just takes care of us, and it goes sensory neuron, reflex arc, motor neuron, move. Right? Sometimes you just got to move. This example is showing an apple. An apple's not like a serious crisis, but it could be a crisis. And you've got to move faster than the brain can process. So that's what reflex arc is there to protect us. Another example of reflex arc is the gate control theory. Now, this exists in the spinal cord. In the spinal cord in the central nervous system, sometimes we can control our muscles by pure instinct without having to consult the brain for major decisions. Again, if you have an accident, a wall is coming down, we're in an earthquake, you've been in a car accident, your hand is on a hot stove. If you're in a serious situation, the gate control theory and reflex arc are going to take over. So the spinal cord can take over and just go, no, move now, move your legs now, move your arms now, get going now. And we don't have to have a whole lot of thought. Sometimes people, when they've been through an emergency, and they'll tell you afterwards, they'll say, I don't even remember processing this, right? It just happened so fast. It just happened so fast that I was lifting the car, or it just happened so fast that I was moving something. They don't even consciously know how they did it. And that's because of gate control theory and reflex arc. All right, and now we're prepared for class. So we're going to do the rest together.